A lot of news around quantum computing from the past 5 to 10 years has focused on how current web encryption methods will become obsolete in the age of quantum computing. Could you explain this?
Yeah, so this is actually one of the maybe most famous quantum algorithms for the moment, and it's based on Shor's algorithm. Peter Shor invented or published this in 1994, and it's a method for factoring large integers into their prime number constituents. And this might seem like, okay, yeah, cool. So what? But actually, this is a mathematical problem that most of the asymmetric encryption, this public key encryption, is based on, and that's then what is used in online banking and web traffic for the moment. And so this comes from a mathematical fact that multiplying two integers with each other is really simple. No matter how large they are, like a normal computer really quickly can solve this problem. And but the reverse problem, finding out from a large number which two integers was this product of, is extremely hard. And so much of modern day encryption is based on this asymmetry in this mathematical problem, that it's easy to multiply two numbers, but then after that multiplication, figure out if you don't have those two numbers, what were they, is very difficult. And for example, this RSA 2048, which is one of the most used encryption standards for the moment, at its core, it's based on multiplying two integers that are about 300 digits long to produce about a 600 digit long number, and relying on that, the reverse engineering of this after you only transmit the 600 digit long number will be impossible for modern computers to crack. And it is true. So even the most powerful supercomputer would take several times the age of the universe to really try to figure out the prime number factors of a 600-digit long number. But what Peter Shor then showed in 1994 is that if you would have this quantum computer that still then was a theoretical concept, then also the reverse problem would be really easy to solve. And this really is based also on this massive parallelism that the quantum computer can provide through superposition and entanglement and so forth. And this really maybe also served as a wake-up call for many actors around the world. It showed really the latent power that quantum computers can have when they are sufficiently mature, but it also then, of course, showed the threat to encryption as we know it and as we use it to a large extent these days. So it is definitely a real thing. For the moment, we are still very far away from having quantum computers that would be powerful enough to really pose any sort of threat to factorizing. It has been estimated you would need about 20 million qubits to do this, 20 million noisy qubits, and now we are at the stage where one is developing 1,000 qubit processor. So we are in a way quite far from it still, but we are getting there, and we should remember that and keep in mind that how long do we want our secrets to stay secret. So there is already this suspicion that the many actors are just downloading encrypted information now just to decrypt later. And of course, if you have information flowing around the internet that you would like to be kept secret for, let's say, 20 years, 30 years, some medical data, or even then state secrets if you go to that level. So we really are at the stage when one has to start to transition to quantum safe cryptography. So we need to change the encryption algorithms that we are using, just in case the quantum computers become ready quicker than we thought, and even if it would take this 50 years even before they are ready. So yes, it's a real problem and it has to be tackled. But I would say for normal people is not that urgent. That's something that we have to do at infrastructure level, but it is a big process, just changing all the routers in the world to be able to handle new algorithms. So for example, this quantum resilient or post-quantum algorithms, so they do exist already, but they have not been completely standardized yet, and so there is a long administrative process already into getting some new encryption algorithms deployed all around the world. So it's a work that has to be started now, and so it's definitely a real thing.
It's really interesting, and you know how some inventions kind of just come as a surprise. Somebody invents it and it has a disruptive force. But this horizon has been we've been going towards it for the past decade or even longer. We've seen it, and we know that there's this kind of horizon coming up that could break modern encryption, but then we just don't know when it happens or when we reach that horizon.
That is I think also a problem for actually getting now your act together and start doing something, is that it's sometimes in the future. So in a way, it's a bit similar to this Y2K bug, the year 2000 bug.
Yeah,
but that was much simpler because then you had a definite deadline. You had to have it ready by the 31st of December 1999. Otherwise, your computer system broke the next day. But here, where there's no definite time, so then it is maybe too easy to do. Okay, let's do it next year, instead of starting now. But it is a challenge, and it is also just this, in a way, a mental challenge for getting oneself to really the drive to, okay, now we have to do this. But that's also why it probably needs to come from just higher level, that someone puts in place that now all the banks have to change their encryption method. So it has to come from legislation, because of course many are already exploring this and starting to implement it, and there are products that use this, but really this final push of now we just do it, because it's something that has to be done anyway. So, and the sooner we do it, the better. Some say we are already a bit too late, considering this that some encrypted information should stay encrypted for a long time, and so we really just, as a society, technological society, we just need to just change the algorithms.